Hello, my name is Dawon SUH, a member of the KGSEA Math Circle. Today I'm going to talk about quantum computing. By the end of this talk, you should be able to explain in your own words why quantum computers can be much faster for certain problems, what physical ideas make that possible, and what kinds of problems actually benefit from this approach. Before defining anything, I want to start with a scene you probably know. In the film Infinity War, there's a scene where Doctor Strange says he has seen 14,605 possible futures. Obviously, this is fiction, but the type of problem he's facing could be very real. He's dealing with a situation when the numbers, where the number of possible outcomes is so large that trying them one by one simply doesn't make sense anymore. In a sense, he succeeds precisely because he doesn't explore futures sequentially. He behaves as if he's using a quantum way of computing. This kind of situation is exactly where people start asking whether we need a fundamentally different model of computation. So here's the question that will guide the entire talk. What if a computer could explore many possible answers at the same time? To make that concrete, think about chess, mazes, or password guessing. In each case, the difficulty comes from how fast the number of possibilities grows. If a problem has two choices at each step, then after n steps, the number of possibilities is 2 to the power of n. That growth is exponential. A classical computer, no matter how powerful, checks possibilities one by one. If you double the hardware, you can check roughly twice as many cases per second. That's linear improvement. But 2 to the power of n doesn't grow linearly. It grows much faster than any realistic increase in hardware. So even if you add more processors or make them faster, the number of possibilities still outpaces what the computer can handle. And this mismatch, linear computational growth versus exponential problem growth, is why classical computers fundamentally hit a wall. At this point, we can finally define the basic units. A classical computer uses bits. A bit is always either 0 or 1. A quantum computer uses qubits, where a qubit is a physical system described by a quantum state. A helpful analogy is a coin. A classical bit is like a coin lying flat, heads or tails. A qubit is like a coin spinning in the air. Before you look, the state contains both possibilities. This already hints at something new. Information itself is being represented differently. And to make this precise, I'll introduce just one piece of notation. We write the basic states as ket 0 and ket 1. A general qubit state is written as psi equals a times ket 0 plus b times ket 1. And the crucial point is that a and b are amplitudes, not probabilities. And the probabilities come from squaring them, and the total must add to 1. This is where quantum mechanics enters the picture and where we are no longer computing with probabilities, but with amplitudes that can later combine. And this idea is called superposition. A qubit can represent multiple possibilities in a single state, but it's important to clear up a common misunderstanding. This is not simple parallel computing where you get all the answers at the end, because you don't get to read out every possibility. You measure once and you get one outcome. So the real problem becomes, how do we design the state so that the single outcome we observe is likely to be the useful one? Let's talk about measurement directly. When you measure a qubit, you don't see a little 0 and a little 1. You see exactly one value. And that's why people say the state collapses. A helpful analogy here is an exam. While solving a problem, you might explore multiple approaches in your notebook. But when you submit one final answer. And quantum computation works the same way. The computation is everything that happens before measurement, and the measurement is the final submission. This is where Schrödinger introduced his famous cat. The experiment wasn't meant to be realistic and was rather designed to make people uncomfortable. If superposition is real, why don't we see these effects at everyday scales? The point here isn't the cat. The point is that measurement plays a fundamental role in turning possibilities into reality. And for quantum computing, this means algorithms must be designed around measurement from the very beginning. At this point, physicists discovered something even more surprising: entanglement. Entanglement means that you can no longer describe parts of a system independently. The system has to be described as a whole. A standard example is if you measure one qubit, the result looks random. If you measure the other, also random. But when you compare results, the correlations are extremely structured, and information is no longer stored in individual qubits, it's stored in relationships. This immediately raises a concern. Does entanglement allow faster than light communication? It does not. And here's the little key distinction. Correlation is not communication. Each local result is random, and the correlation only appears after you compare results using classical communication. So relativity remains intact. What changes is now how information is organized. Now we can introduce the third ingredient, interference. Because we are working with amplitudes, different computational paths can combine, and some paths reinforce each other and others cancel out. And quantum algorithms exploit this by designing interference patterns that suppress wrong answers and amplify correct ones. This is the core mechanism behind quantum speedups. And these ideas are not just theoretical. There are real quantum devices built on different platforms, superconducting circuits, trapped ions, and photonic systems. And organizations like IBM Quantum and Google Quantum AI are actively building and testing these machines. The most important metric today is not just how many qubits exist, but how many can operate with low error rates. But the biggest obstacle in this field is noise. Quantum states are extremely fragile, and therefore small disturbances destroy the information we're trying to preserve. And that's why error correction and stability are essential. One interesting research direction here is time crystals. Time crystals are non-equilibrium quantum systems that show remarkably stable, repeating behavior under periodic driving. They are not about time travel, and they don't prove that time itself is discrete. What they show is that quantum systems can maintain time order structure even in noisy environments, a property that may help with stability and synchronization in quantum hardware. So where could quantum computing matter first? Cryptography is one area driving the transition to post-quantum security, and chemistry and material science are another because molecules are inherently quantum systems. Optimization is often mentioned as well, logistics, scheduling, but expectations should be careful because real-world constraints still matter. Quantum computing is most promising when the problem is naturally tied to quantum structure or massive state spaces. And before I end, I want to change the scale of the discussion. Today's quantum computers are small and noisy, but imagine 10 million stable error-corrected qubits. That wouldn't just make current computations faster, it would move us into a regime where we can represent and manipulate state spaces that are currently out of reach. And that shift alone could make entirely new classes of problems accessible. And if you want to go deeper into this topic, the path is as follows. In mathematics, linear algebra and complex numbers are essential. In physics, quantum mechanics and quantum information explain what these states mean. And in computer science, algorithms and complexity theory explain why speedups are even possible. And if you want hands-on intuition, tools like Qiskit let you experiment with simple quantum circuits and see these ideas in action. Thank you for listening.